Hello everyone. This is going to be section 2.3, and in here we're going to see some techniques for computing limits. Now, in the conclusion of the previous section, we were tying the existence of the limit to the existence and the equality of the side limits. Okay, so this was meant that if we had this function here, for example, an equation of the line, and we were approaching to, let's say, a point A by the left side, then this was going to a certain point, and in here we're approaching to f of a. This is a continuous function, and if we take a look at the side limit approaching a for the right side, then we notice that the function is also going to approach f of a. So the general idea is that for one function where the limit is cis, the side limits is cis, and they are the same thing. Okay, and not only that, but they are equal to the function in this case, in this particular case. So it is very nice to have the fact that the limits is cis and they're equals to the function. This is what happens when we have a continuous functions. And having a continuous function is going to allow us to do some extra things and to evaluate limits in a better way. So given that assumption, given the assumption that f of x is continuous and it doesn't have interruptions, then we can use the algebraic definition of the function to calculate some limits. For example, here, if we assume a line like the one we just did, lines are continuous, and so the limit when x goes to a of f of x is going to be f of a, which is the same as saying m times a plus b. So in this case, when the function is continuous, we can say that the limits, or that the general limit is equal to evaluating the function, which was not the case in general. Okay, so having a continuous functions is going to be a big deal for just calculating functions using the rule, calculating limits using the rule of the function. Okay, so let's take a look at what happens if we have that particular property. Now with that we can do algebra in the limits. So, and by doing algebra, I mean we can do sums, difference, multiplication, quotients, all that kind of stuff. Okay? So if we're assuming that the limit when x goes to a of f of x is cis, and the limit when x goes to a of g of x is cis, then we're going to have the following properties. Okay? We're going to have that the limit of the sum of two functions is equivalent to just the sum of the limits. Similarly, with the difference, the limit of a difference of two functions is just going to be the difference between the limits. And if we have a constant multiplication of a function and we take the limit, is going to be the same that multiplying that constant by the limit. Okay? So more properties hold, but let me show you an example. So we have limit when x goes to 0 of the function e to the x plus 7x plus 3. Notice that in here we are under the assumption that this is a continuous function. Indeed, this is a continuous function. So what's going to happen is that we can just break the limit in the sum. This is a sum of several functions, or we can see it as a sum of several functions. And so now this will be the limit when x goes to 0 of e to the x plus the limit when x goes to 0 of 7x plus the limit when x goes to 0 of 3. Now we can evaluate in each of these functions because each of these function is continuous. And so notice that this is just e to the 0, which is f of 0, 7 times 0, which will be the function 7x plug in 0, and 3, which will be the constant function 3 plug in 0 again. Now e to the 0 is 1, n plus 3 is going to become 4. This disappears because it's multiplied by 0. Now let's take a look to another example with a difference. We have the function e to the x minus sine of x. So both the functions e to the x and sine of x, they're continuous, they don't break anywhere. So we're going to be able to use the difference in the assumption of the continuity. So doing that, this can be seen as the limit when x goes to 0 of e to the x minus the limit when x goes to 0 of sine of x. Okay? And tacitly, what that means is that we can just say, well, this is going to be e to the 0 minus sine of 0, right? We can just plug in the 0 because the assumption of continuity, and this is just going to be 1 minus 0 and 1. So these are the properties of the limits operating behind. Now we can see the third property of in operation really easy in a function like this, like in a linear function. If we have limit when x goes to 0 of 7x plus 3, I can split this in 7 times the limit of x plus limit of x going to 0 of 3. So notice that this part here, this little bit here, is using the property of getting out the scalar that is multiplying. So the 7 that is multiplying here. Okay? So with this rule, I can really now start doing limits with sums. And so do I need to go over all the work that I'm doing here? Maybe I can simplify it a little bit. And so let me show you how that will look like. Let's assume that I have limit when x goes to 1 of x squared minus 7x plus 1. This is a polynomial function, and I'm going to assume it's talking about the function, of course, f of x, x squared minus 7x plus 1. Because I assume that this is continuous, then this limit is going to be equals to f of 1. So I can just essentially say, well, this is just going to be 1 squared minus 7 times 1 plus 1, which is essentially the same thing that I get if I split this limit in all the pieces that I can, right? Okay, so this is essentially doing the same thing, and I can arrive to the same point. Now, that's not the only property that we can get. We can get at least 4 more properties here. The product also works. The quotient works with a restriction, and we're going to have behaviors for the powers and the roots. So let's take a look at that. In the product, if we take in the limit of a product of 2 functions, there essentially what we can do is say, well, that's going to be equals to the limit, the product of both limits, like it's in here. So I can separate things. And with the quotient, we gotta be careful. We just gotta be really mindful that we don't have a denominator that becomes 0 when we're taking the limits. When we'll plug in the function in this point A, this cannot be 0. Okay? So if that doesn't happen, then I can say, well, the limit of a quotient is just the quotient of the limits. Okay? Now, in terms of powers, is much more simple, and a root is a power as well. So what's going to happen is if I take the limit of a power function of certain function power to the n, then what I can say, well, that's going to be the limit of the function, and all that limit power that to the n. Since the x to the n power function is continuous, then we can translate that to this. And similarly with the root, instead of making the limit over the whole root, what we can do is take the limit over the function and calculate the root after. Okay, so let's take a look at this type of things in action. Okay, so I had an example here. Now let me do limit when x goes to 2 of x squared plus 2 x plus 1. So the first thing that I gotta check is this going to cause issue in the denominator? Notice that this is a 2. So notice 2 plus 1 is going to be 3. So no, it's not going to cause any issue. So because of that, then I can just split this as this. Right? And now I can see, oh, this is continuous, this is continuous. So no issue in any of that. This is going to be 2 squared plus 2. And this over here is going to be 2 plus 1. So I get my end result, which is going to be 4 plus 2 over 3, or 6 divided by 3, which is going to be 2 at the end. Notice that that is going to be a different thing if I do the following. If I do now limit when x goes to 2 of x squared minus 4 over x minus 2. Okay? Notice since limit when x goes to 2 of x minus 2 is equal 0, in here the bottom is 0. So I can't really do the same thing that I did here. I can't just plug right away. In particular, in this case, notice that something else is happening, and it's that not only the bottom is becoming 0, but the top is becoming 0. So I have something that is called an indeterminate form, a 0 over 0 form. When you have this type of limit, which is a 0 over 0 form, it means that you need to do something else to find out what the limit is. Fortunately, what we're going to do here is something really simple. We're going to do a factoring. We're going to use difference of the squares. So this x squared minus 4 can be factored out as x minus 2 times x plus 2. Okay? And so if I do that, notice that this stops becomes this, but notice that this is a factor here is the same thing that here. So I get to cancel that, and that becomes limit when x goes to 2 of x plus 2. Now this is a continuous function, and this is just going to give me 4. So this means, this implies that the limit when x goes to 2 of x squared minus 4 over x minus 2 is equals 4. Okay? This is not going to be the only scenario where things like that are going to happen, and we're going to see that later. But before that, let me do another example with the power and the root. So now, let's take limit when x goes to 0 of 2 sine of x, and I'm going to have square root. Okay? So because the square root is just a power in itself, this is a power to the 1/2, I can see this as limit when x goes to 0, and this is 2 sine of x to the 1/2. This is what this second root means. And then later, what the rule of this is saying is, look, the root is continuous, so you can just do limit of 2 sine of x, and then everything to the 1/2. Okay? And now this inside is a continuous function. Sine of x is a continuous function, so I can just do this and say this is 0. And so now this is going to be 0 to the 1/2, and the whole thing is going to be 0. Okay. Another example. Limit when x goes to 1 of 1 plus 1 over x power to the 3. Notice this is power to the 3. Again, we can use the same thing that we did just now and operate with the rule of the limit. This is limit when x goes to 1 of 1 plus 1 over x cubed. and then we use the limit. Notice that 1 is not going to cause issues. There's no problem in 1. This is a continuous function, and so this means that this is 1 plus 1 cube, or 2 cube, which is 8. Okay, so this is a couple of examples of the use of these properties. Of course, once that you get comfortable with this, you don't necessarily have to show the properties, but you can jump immediately from this to this and to this and keep going. Okay, now let's continue with some other properties. Now, if we're talking about polynomial functions, in polynomial functions, we assume that those functions are continuous because they are by definitions. So we're always going to have that this limit when x goes to a of p of x is p of a. However, when we have rational functions, so we have a quotient of two polynomials, there we have to be careful as well with not having a root of the polynomial below here in the limit. Okay, so we gotta be careful that a is not a root of polynomial q. Now, with that, I can continue talking about what happens if I do one-sided limits. So all the rules that I previously mentioned work in general, but now we gotta be especially careful with what happens if we have one-sided limits. And so if we're approaching by the left or by the right side, we gotta be careful that if whatever is inside is positive or negative. Okay? Do you guys remember that the square root of a negative number does not exist in the real numbers? It's a complex number, right? So same thing here. 1 over n is the nth root, right? So if this n is even, we need that whatever is inside in this limit is positive. So provided that f of x is 0 when x is near to a, when we're approaching by the right side, if we have this, then everything is going to be all right, and we can say, yeah, the root of f of x is the limit of the root of f of x is equals to the root of the limit of f of x. Similarly, if n is even, we're gonna have the same thing, but we also have to check if f of x is still positive when we're approaching by the left side. Okay, and so that's what happens, and we have issues in there. If n is odd, then we're not gonna have any issues. Okay, and that's gonna be okay in any of the cases, but we just gotta be careful with n is odd. Now, let's take a look to an example, and at the same time we're going to use a piecewise function, and we're going to check those limits. So in here we call something a piecewise function if we have that it is a function up to a certain point and there is another function after a certain point. So if you notice here in this f of x definition, you see that before x is 1, this is going to behave like minus 2x plus 4. So essentially from minus infinity to 1, it behaves like this equation of the line, minus 2x plus 4. Now if x is bigger than 1, so from 1 onward to infinity, then this function is going to behave as the square root of x minus 1. Now, let's take a look of what is the limit in each of the cases. Notice that clearly, because you can see from the graph, when we're approaching by the left side to 1, then we're going to have that the limit of f of x is 2. You can do this in the same way. You can see it from the graph, but you can also block when you're approaching 1. This is almost continuous here, so you can approach with values closer to 1, and you're gonna see that this is getting really close to 2. If you actually plug in 1, you can see here that minus 2 plus 4 is 2. And so you see that they're approaching to 2 here, which is actually the definition of the function as well. But now when we're approaching 1 by the right side, notice that we're going over the square root. And in this case, if we're being approached by values that are larger than 1. And so because they're larger than 1, they're 1.1, 1.2, then whatever is inside of the square root is going to be positive. And so this side limit is this, and you can notice that it's approaching 0 really fast. The more that you move to the right side closer to 1, the more that it approaches 0. So in this case, the general limit is not going to exist, and the side limit by the left is 2, the side limit by the right is 0. Okay? So this is how you approach piecewise function limits. Now, it's worth mentioning that there are the difference with the functions. I'm stressing this out a lot because with the rules of calculation, we assume that we have continuity, but that's not always true. Notice this example here. This is continuous everywhere but in 1. So it breaks at 1. You could calculate any limit at any different point with any of these rules. So if you're doing -1, you only need to use this function. If you're using 2, you only need to use the root function. But at this point of breaking, then it's more complicated and you need to do the side limits. Okay? And now notice that when we have discontinuity, the limit is different from the function evaluation. In this case, for example, we have that the function evaluation is this, which differs from what the limit is approaching. Here the limit is approaching a quantity that is over here, but that differs from the value of f of a. Sometimes we don't even have value of f of a, like in this case. So sometimes the limit exists, but the function is not defined. So don't forget about that. Now, when we have rational functions, we can always factor out and try to simplify them more than we can if it's needed, and especially in the cases where we have things like zeros in the denominator. So the special case that I just showed in the previous exercise, it was called algebraic simplification, and this is going to be another example of that. So now f, and this is going to be limit when x goes to when x goes to 2 of x squared minus 6x plus 8 over x squared minus 4. So first notice that if you plug immediately to here, this is going to become a 0. So this is from the form, let me just write it out. This is 0 on the denominator. And if you plug it to here, you get 4 minus 12, which is minus 8 plus 8. That's going to be 0. So this is a 0 over 0 again situation. So what we do in this case is we try to see if we can simplify. So we factor out two numbers that multiply give me 8, but the sum gives me minus 6. So x minus 2, x minus 4. Okay, minus 2 times minus 4 is 8. Minus 2 plus minus 4 is minus 6. Okay, I can simplify the bottom as a difference of the squares. Hope you remember that from your pre-calc. And then we get this. We get that this is now limit when x goes to 2, x minus 4 over x plus 2. Notice that this is now a continuous function because it doesn't have an issue, doesn't become 0 here. So the top is minus 2, 2 minus 4 minus 2 over 4, and that's going to be minus 1/2. So that'll be the solution to this limit.